Let's look at the energy diagram of a spring. Okay, so in this case, my potential energy depends on my how far the spring is stretched. So in this case, they're putting that equilibrium point at x equals 0. So I really could just consider this x squared. And so my potential energy graph looks like a parabola because it goes like x squared. And we can kind of say the same things about it. In this case, here is my total energy line, my total mechanical energy that's equal to kinetic plus potential, and it's constant. And so as what I can say here is, this is the maximum x position that the spring will ever be at. This is the farthest it can go in the positive x direction, and this is the farthest it can go in the negative x direction, because at this point, all of that mechanical energy I have has turned into potential energy, and my speed here is 0. It's when the object turns around. Now as the object goes back to smaller and smaller x values, we're gaining kinetic energy. That means the mass attached to that spring is going faster and faster and faster and faster. Here, at this point, my equilibrium point, all of the energy of the object is kinetic energy. There's no potential energy because this is right when the mass happens to pass that equilibrium position. This is right when the spring is not stretched or compressed. All of my energy here is kinetic energy. And now I'm starting to go in the other direction. Maybe I'm stretching out the spring now. And so I'm going to start losing kinetic energy. So my kinetic energy is getting smaller and smaller and smaller as I slow down and slow down. My potential energy is getting bigger and bigger and bigger as that spring is stretched more and more and more. And eventually I've run out of kinetic energy. All of my energy is potential energy. This is when the object comes to rest. And now it's going to come back and start getting pulled back towards the equilibrium again. So again, we're just describing the behavior of a spring in ways that we've already talked about and ways that we might understand, but I'm just looking at it in terms of a graph. So here is some fake potential energy. It's not something we've seen before. It's not a spring. It's not gravity. It's just some unknown potential energy. And this is what that potential energy looks like in space, meaning what it looks like is a function of position. So, the book goes through and talks about all these different points on the graph. But what I want to point out are some very important points on here. They're called equilibrium points. So if this graph, this red line, is the potential energy, we've already said that if you take the derivative of the potential energy with respect to position, if you do like du dx, the negative of that is your force. Okay? So that's like saying the slope of this line is the force. Except here, this is a positive slope. Oh, no, wait, sorry, that's a negative slope. This is a negative slope, and whatever the value of this slope is, and then negative, if you take negative of that negative, you would get a positive for my force, and that means the force is pushing this object in the positive direction. Okay. Here I have a positive slope, and so the force is equal to the negative of that. So that would be a negative force, meaning when the object is like at this position, it's going to feel a force in the negative direction, pushing it towards more negative x values. But another thing we can say is that at this point right here, and at this point right here, and at this point right here, the slope of that potential energy graph is 0. That means at this point, when the object is right here, the force on the object is 0. And when the object is right here, the force on the object is also 0. And when the object is right here, the force on the object is 0. So we call these 3 points here equilibrium points, because those are the positions that the object can be in and there's no force on it. The force on it is 0. Okay. This point specifically is called an unstable equilibrium point. It's unstable because if you go a little bit to the left, you're going to be feeling a force that's going to be pushing you to the left. And if you go a little bit to the right, you're going to feel a force that's going to push you to the right. So the forces that you feel push you away from that equilibrium point. These points down here are called stable equilibrium points because they kind of are the opposite. If you go a little bit to the left, you're going to feel a force to the right pushing you back towards the equilibrium point. Here, if you go to the right of that equilibrium point, you'll feel a force to the left pulling you back. So this is called a stable equilibrium point. So a good way to kind of imagine what these potential energy diagrams show you is you can almost imagine that this red line is like the shape of a hill. And then you can imagine, the location of your object would be like putting a ball on the hill at that point. So if you have a hill shaped like this, if you put a ball right at the top of the hill and let go, if you get it perfectly centered there, the ball will not move. It will be in equilibrium. It will not roll to the left and it will not roll to the right. But if you displace it a little bit, then the ball is going to roll down the hill over here. And if you just place that ball a little bit to the right over here, now the ball is going to roll to the right over here. So this hilltop right here is called an unstable equilibrium point, because if you're just a little bit off from that equilibrium, your object is going to move away from that equilibrium. Whereas if you imagine having a ball and putting it right here at the bottom of this little valley, if you get it right in the middle, the ball's not going to move. That's my stable equilibrium point. But if you miss and you just place it just a little bit to the left, now that ball is going to roll to the right, back towards the equilibrium. If you displace the ball to the right a little bit over here, the ball is going to roll to the left, which is again rolling it back to that equilibrium point. So that's why we call these types of points stable equilibrium points. And this type is called an unstable equilibrium point. Here's an example working with an energy diagram. So press pause, take some time, try to work through this, and then press play when you want to go through it with me. So let's first look at what we're told. We're told that when the particle is at the position x equals 2 meters, it has a speed of 4 meters per second. Well, before I even look at my graph, I can figure out how much kinetic energy the object has. And since we're dealing with energy, that's a good thing to try to calculate. So I'm going to calculate how much kinetic energy the object has. The kinetic energy is equal to 1/2 mv squared. And here I've plugged in the mass and the speed they told me, because when we're at the position x equals 2 meters, we have a speed of 4 meters per second. Plugging that all in, I find that my kinetic energy at this position is 4 joules. The question is asking me for the total mechanical energy, and total mechanical energy is the sum of my kinetic energy plus my potential energy. And this red line here represents my potential energy. So I'm going to look at the graph at the position x equals 2 meters, that's right here. I have 1 joule of kinetic energy. Sorry, of potential energy. Potential. So to calculate my total mechanical energy, that's my kinetic plus my potential. So I have 4 joules of kinetic energy plus the 1 joule that I find from this graph. So my total mechanical energy is 5 joules. And if I wanted to, I could draw a line up here at 5 joules of kinetic energy, and this black line here represents my total mechanical energy, which remains constant regardless of where the object is. Now the next question says, where will the particle turn around? So my turning point happens when my total mechanical energy line crosses my potential energy line. And that's going to happen right here at a position of x equals 10 meters. And then finally, the last question asks, how fast is the particle traveling when it is at the position x equals 6 meters? So when we're at this position right here, just by looking at my graph, I can tell that I have 3 joules of potential energy, which means I have 2 joules of kinetic energy. So I'm going to use the fact that I know that I have 3 joules of kinetic energy from this graph, and that means that I have 2 joules of kinetic energy. So I'm going to use that to calculate what my speed is. So I can say K is equal to 1/2 mv squared, and K is equal to 2 joules. So I plug that in, and then I plug in the mass, and then I can solve for my speed.